Hello, this video includes information on electrochemical cells.
So we're going to look at a simple electrochemical cell. Sometimes it's called a galvanic cell or a voltaic cell. And it's just an electrochemical cell that's a spontaneous redox reaction that produces an electric current. Okay, so over here, this is our anode compartment. And oxidation takes place in our anode compartment. So we've got a copper ion solution and we've got a copper electrode. And the copper atoms on that electrode are losing electrons and becoming copper ions in the solution. So the concentration of copper ions in the solution are going up. The mass of the copper anode is going down, and electrons are being generated at the anode. Okay, this side is our cathode compartment, and reduction takes place in the cathode compartment. Now, a way to remember that, anode and oxidation both start with vowels. Okay, so oxidation takes place in the anode compartment, and then the reduction takes place in the cathode compartment. So we have a silver ion solution and we have a silver electrode. In this case, the silver ions in the solution are gaining electrons to become silver atoms. So the concentration of silver ions in the solution are going down, and the mass of silver on our cathode is going up. Now, the two electrons that are lost by the oxidation over here are going to flow through this wire over to the cathode compartment, where they're going to be used in the reduction reaction. So we have a chemical reaction taking place. We have a redox reaction taking place. But because the oxidation half reaction is in one compartment and the reduction half reaction is in another compartment, and we connect the two half reactions together, we're going to cause a flow of electricity and electric current due to a redox reaction. We can denote this with what's called a cell notation. We do the oxidation part first. So we've got the copper going to copper ions, kind of just denote it this way, it's just shorthand. We do the reduction second. Okay, we've got silver ions going to silver atoms. And this double line here just represents the fact that the anode compartment is separated from the cathode compartment. So this is a shorthand way of writing this overall reaction or drawing this whole electrochemical cell out. And there is this salt bridge here. And what the salt bridge does is it keeps everything neutral. So as the electrons flow from the anode to the cathode, the anions flow into the anode compartment to keep it neutral. And as the electrons flow into the cathode compartment, we're building up negative charge here. So the cations flow into the anode compartment. So the electrons flow from the anode to the cathode, alphabetical. Electrons always go from A to C, okay? From the anode compartment to the cathode compartment, or from the oxidation half reaction to the reduction half reaction. And just by convention, we put the anode compartment on the left-hand side and the cathode compartment on the right-hand side. So the electrons are flowing from the left compartment to the right compartment. The electrode in the left compartment is the anode, and that's where oxidation takes place. Again, A and O are vowels, just a way for you to remember it. And the reason why it's called the anode compartment is because the negative ions or the anions from the salt bridge flow into that compartment to keep it neutral. And when we look at the right-hand compartment, it's the cathode compartment. The cathode compartment is where reduction takes place. And the reason it's called the cathode compartment is because as the negative electrons build up on the right-hand side, cations flow into the cathode compartment to keep it neutral. That's why it's called the cathode compartment. Now, the cell potential, okay, can be read off of a voltmeter. Okay, it told us for this one it was 0.46. Okay, and it results from the fact that the two half reactions have different cell potentials. And the salt bridge is there just to keep everything neutral, to keep a closed, complete circuit, and allow the electrons to flow, allow the current of electrons to flow from the anode compartment to the cathode compartment. We're given this cell notation. We want to determine what's being oxidized, what's being reduced, what's the oxidizing agent, and what's the reducing agent. Okay, so the substance that's oxidized is going to be losing electrons, and the oxidation number or the oxidation state is going to be going up. So magnesium going to magnesium ions, or copper ions going to copper atoms. Which one is being oxidized? Magnesium or copper ions? So magnesium is being oxidized because it's losing electrons. Copper is being reduced because it's gaining electrons. Now, we actually didn't talk about the terms oxidizing agent and reducing agent yesterday. So the substance that's oxidized is losing electrons. And when it loses electrons, those electrons are going to cause something else to be reduced. So the substance that's oxidized is the reducing agent. The substance that's reduced is gaining electrons, which means it's causing the other substance to lose electrons. It's causing the other substance to be oxidized. So the substance that's reduced is the oxidizing agent. They're just opposites. So since magnesium is being oxidized in this example, it's the reducing agent. I think I actually wrote that down somewhere. Since magnesium is being oxidized, it's the reducing agent. And since copper is being reduced, it's the oxidizing agent. Okay, they're just opposites. The substance that's oxidized is the reducing agent. The substance that's reduced is the oxidizing agent. All right, so let's look at these examples. Okay, we want to write the following balanced reactions in their cell notation, in their shorthand notation. So the oxidation comes first, and the reduction comes second in our cell notation. So look at this reaction. Silver ions or copper atoms, which are being oxidized? Which one has the oxidation number going up? Silver ions or copper atoms? Silver ions. Silver ions are going from a +1 on the reactant side to a 0 on the product side. That means silver ions are being oxidized. Okay, they're being reduced. I'm doing this backwards. Sorry, +1 to 0. Silver ions are being reduced. Okay, the copper is going from a 0 to a +2. That means the copper is being oxidized. The oxidation comes first in the cell notation. So our cell notation would be the copper atoms going to copper ions. Okay, this is showing the oxidation half reaction. And then the silver ions are going to silver atoms. This shorthands the reduction half reaction. And this double line here essentially means that the oxidation is taking place in one compartment, which we said is the anode compartment. And the reduction is taking place in the other compartment, which we said was the cathode compartment. So using this A as an example, let's look at B. First, the nitrate's a spectator ion, so don't worry about the nitrate here and here. Okay, we've got manganese going from atoms to ions, and the charge on the magnesium is a +2 here. So it's going from a 0 to a +2. Think about what that means for the manganese in this redox reaction. The tin is going from a +2 charge to a 0. Think about what that's doing to the tin in this redox reaction. And then write your cell notation. Remember that the oxidation comes first in your cell notation, followed by your reduction. All right, so we've got manganese atoms going to manganese ions. Here's our oxidation. This is what's taking place in the anode compartment. We've got the tin ions going to tin atoms for our reduction side of our cell notation. And this is what would happen in the cathode compartment. So this is our shorthand cell notation for this reaction. All right. So now let's talk about these galvanic cells and spontaneity. When we talk about galvanic cells, sometimes they're called voltaic cells. They take place spontaneously, but we need to decide which direction is the spontaneous reaction taking place. So what we use are what are called standard reduction potential values to help us to decide which way the reaction is favored. Is it favored in the forward direction or towards the right? Or is it favored in the reverse direction towards the left? So what we have here is kind of a short abbreviated activity series or a reduction potential table. So it lists various substances and they're gaining electrons. So these are all written as reduction half reactions. And we're given the potential for this reaction to take place. The more positive the number is, the stronger the oxidizing agent, or the more likely it is to be reduced. The more negative the number is, the stronger the reducing agent, or the more likely it is to be oxidized. And we're going to use that information to decide whether or not a reaction is spontaneous or not. So the potentials for the half reactions are measured in volts. Okay, so the V here are the units that we're using for our standard reduction potential values. And they're all relative to a hydrogen gas electrode, which we're going to look at in a second. And if the voltage is a positive value, the reaction is going to be spontaneous. Okay, so before we go through whether it's spontaneous or not, let's just do a little bit of a talk on electricity. So when we talk about cell potential, okay, the symbol that we use for cell potential is a capital E. The units are volts, which is a capital V, and it's essentially a measure of the difference of the electrical potentials between the oxidation half reaction and the reduction half reaction. When we use the term current, the symbol that we have for current is a capital I. The units are amps, which is a capital A. And it's a measure of the flow of electrons through a wire. And when we talk about resistance, the symbol for resistance is a capital R. And the units are ohms, this is a Greek unit for that. And it measures the resistance, the impediment of the flow of electrons. Okay, so to kind of summarize this up, this is just an example. It's not talking about electrons, but maybe it'll make more sense. Okay, if we have a cup filled with water, and let's say we have it filled to here, and we have a hole, okay, a little bit of the water is going to flow through that hole. If we have our cup of water and it's filled to here, we're going to have more water flowing out of that hole. The difference in the height is the difference in the pressure that causes the water to flow out of this hole. Okay, that's kind of like what we mean when we talk about voltage or our electrical potential. The difference between this value here and this value here. The current is kind of like the flow of the water out of this hole. Okay, the more water that flows out of the hole, the larger the current. The less water that flows through this hole, the lower the current. It's the same thing as if we talk about the flow of electrons through a wire. If a lot of electrons are flowing through a wire, it's going to be a high current. If a little bit of electrons are flowing through that wire, it's going to be a lower current. And then if this diameter of this hole is really small, there's going to be a great degree of resistance for water flowing through it. If the hole is really big, there isn't going to be as much resistance for the water flowing through it. Resistance is just the push against the flow of electrons. So the cell potential is measured in volts, and it has to do with the electrical potential difference between the reduction and the oxidation half reaction. The current is the flow of the electrons through a wire, and the resistance measures anything that acts in opposition to the flow of electrons. All right, now let's look at standard reduction potential values. When we look at the cell potential, it results from the difference in the electrical potentials between the two electrodes, the oxidation and the reduction. It's impossible to measure the value of electrical potential for just one electrode. So we measure it by a difference, a reference that we use as 0. And the electrode that was chosen as our reference electrode is the standard hydrogen electrode, which just stands for SHE. Okay, we have 1 atm of hydrogen that's being bubbled through a 1 molar hydrochloric acid solution. So in this reaction, we're going to have the hydrogen ions gaining electrons and becoming hydrogen gas. And this has been assigned a reduction potential value of 0. Well, what do we use that for? Now, let's look at a voltaic cell. So over here, this is our standard hydrogen electrode. Over here, we have copper ions and copper metal. So this galvanic cell has our standard hydrogen electrode and our copper ion, copper metal half reaction. Okay, so when we look at the two half reactions that take place, in our anode, the hydrogen gas is becoming hydrogen ions and it's giving off 2 electrons. The electrons are going to flow through our circuit into our cathode compartment, where the copper ions are going to take in those electrons and become copper atoms. 2 electrons lost, 2 electrons gained. Here's our overall reaction. This is the voltage that's read across this cell, okay, 0.337 volts. When we go to calculate the potential difference across this cell, we're going to take the value at the cathode and subtract the value at the anode. The reason why we're subtracting is because the values on the table are reduction values, but oxidation takes place at the anode compartment, and oxidation is the reverse of reduction. So looking at this equation, here's the measured voltage across this cell, 0.337. We don't know what the standard reduction potential would be here. So this is X. But by definition, the value here for the anode compartment is 0. And since we assigned this value as 0, we can figure out what the standard reduction potential is for this half reaction. So what that does is it enables us to come up with values. So I'm just showing you where these values come from. Okay, you're going to be given a table. So here's hydrogen relative to any of these half reactions here, or here's hydrogen relative to any of these reactions here. The reaction that takes place at the cathode is the reduction half reaction. And it'll be the reaction with the larger or less negative standard reduction potential. In the anode compartment, that's where our oxidation half reaction takes place. And that will be the half reaction with the smaller or the more negative standard reduction potential value off the table. Let's apply this. Okay, now that we've gone through kind of, what it all means, let's apply it in some questions. So let's say that we're looking at a standard potential, okay, which is at 25 degrees Celsius, 1 molar solutions, and 1 ATM if we're looking at gases. A spontaneous cell, a galvanic cell or a voltaic cell, will always have a positive voltage. So let's look at this example. Let's say that we have copper atoms reacting with lead ions to form copper ions and lead atoms. Well, the copper is going from copper atoms to copper ions. It's being oxidized. If we look this reaction up on the table, okay, we'd actually be looking up the reverse on the table because the table is always going to be a reduction potential value. We get 0.34 volts. Okay, we just looked that up on a table. If we look up the lead 2 ions going to lead atoms, the table tells us it's negative 0.13 volts. This number here, the 0.34, and this number here, the negative 0.13, these come off the table. It's the reduction potential value for copper ions going to copper atoms, and the negative 0.13 is the lead ions going to lead atoms. All right, to calculate the voltage across this cell, we would take the reduction potential at the cathode and subtract the reduction potential at the anode. Reduction takes place at the cathode, and lead ions are being reduced in this reaction. So for our E for our cathode, we're going to put in negative 0.13. Oxidation takes place at the anode. The copper atoms are being oxidized in this reaction. So we're going to substitute in for our anode negative 0.34. So we've got our reduction value minus our oxidation value, or what takes place at the cathode minus what takes place at the anode, and we get a negative 0.47. The important part is this negative sign. When we look at any type of redox reaction, it will only be spontaneous if the reduction potential value is positive. Since this value is negative, this reaction as written is not spontaneous. It's not going to take place on its own. So let's look at another example. Okay, let's say that we've got magnesium metal reacting with nickel ions, and we want to decide whether this reaction is spontaneous. Okay, well, the reaction at the cathode, which is the reduction half reaction, is going to have the larger reduction potential value. And the reaction that takes place at the anode, which is the oxidation half reaction, would be the one that has the smaller reduction potential value on the table. So this is the information we get on the table. You would just look it up. Okay, you'd look up magnesium to magnesium ions on the table, and the value on the table is negative 0.2372 volts. We look up nickel 2 ions to nickel atoms on the table, and we get negative 0.257. All right, now to calculate the cell potential, we would take the reduction value that takes place at the cathode and subtract the oxidation value that takes place at the anode. So at the cathode, we've got negative 0.57 or 257. We'll plug that in here. We're going to subtract the value that takes place at the anode, or the oxidation, which is negative 0.2372. Okay, subtracting a negative is the same as adding a positive. We end up with a positive voltage difference across this cell. That means this reaction is spontaneous. So magnesium being oxidized and copper ions being reduced will take place spontaneously. As long as the reduction potential difference is a positive value, the reaction is spontaneous. If the value is a negative value, it's non-spontaneous. Let's look at another reaction. Okay, the nitrates are all spectator ions. Iron is going from a +2 charge to a +3 charge. So iron is being oxidized. That's what's going to take place in the anode compartment. The gold is going from a +3 charge to a 0 charge. So the gold is being reduced in this reaction, and that's what would take place at the cathode compartment. We want to decide whether or not this reaction takes place. And again, what takes place at the cathode compartment is the reduction half reaction. So it would be the one with the larger reduction potential value. What takes place in the anode compartment is the oxidation, and it would have the smaller or the less negative, or sorry, more negative reduction potential table. This is what we get when we look on the table. The iron is being oxidized. That's what's taking place at the anode. The table tells us 0.771. The gold is being reduced. The table tells us that's a 1.498. So take the cathode value, subtract the anode value, decide whether we get a positive or a negative value for our reduction potential difference, and decide whether this reaction in the direction it's written is spontaneous. It's the cathode value, subtract the anode value. 1.498 is our cathode value. 0.771 is our anode value. So 1.498 minus 0.771 gives us a positive value. That means this reaction is spontaneous. So what you would need to do to decide whether a reaction you're given is a spontaneous reaction or not is you need to decide what's being oxidized, look up the value on the table, what's being reduced, look up the value on the table, take the reduction minus the oxidation. If the value is positive, it is spontaneous. If the value is negative, it's non-spontaneous.